here and ready to go, and we have the camera. And we won't forget to turn it on today, right? Okay. Some leftover material. If y'all want to go back to signals class. I am going to cover some material that you've seen in 431 before, but we're going to go in a little more detail, and we're going to go faster this time, all right? So, what is that material? That material involves difference equations and difference equations, step and impulse responses, step and impulse responses, and transfer functions. And then eventually, but it won't be today, meaning it'll probably be next Monday, we will get to the topic of frequency responses. So, yes, sir?
You were going to talk about MATLAB as well. I just wanted to remind you for the homework.
Oh, we'll add that to the list too. Okay, what was it we needed to do with MATLAB?
For the homework. So,
I'm trying to remember.
just had to plot and graph functions.
Oh, yes, I will get that. Okay, I'll spend a few minutes on that at the end. Okay, so now I know what I'm starting off with is a review, pretty low-level stuff, but I want to make sure we're all on the same page. So I'm going to write a difference equation here. Actually, I'm going to write two difference equations up here. First one, y of n, is x of n minus x of n minus 1. And over here, I'm going to write another one, y of n minus 1.7 y n minus 1 plus 0.72 y of n minus 2 is x of n. Okay? Two difference equations. And I want you to tell me what terms we have used to describe. Let's start with the one on the left. Y'all remember differential equations, and you talked about order and linearity and all that? What? This is and there's one specific word that distinguishes these two cases. What is that? What?
Order.
Order, okay, let's start with order. This one is a order equals 1. First order. How do I know it's first order? Because I have only one time shift. What about over here? What order? 2. Okay, so this one's second order. They are both linear. They are constant coefficient. And so I'll write, this one's also linear and constant coefficient. What does constant coefficient equation relate to in terms that we use as engineers? Those are linear and time invariant. Yeah, so these two here mean that the systems are LTI. And you remember that's a really nice property for them to have. So constant coefficient is the term we use when we're talking about a differential equation or a difference equation. But in terms of systems, the term we use is time invariant. Okay, what else? We're still missing that one word. What is that one word that distinguishes those two? Notice the difference is that here the output, there are multiple output terms. Over there, there's only one output term. What is the word? I'll get you started over here. This one is non-unique. what? In terms of solving it, remember you just plug in input values and you can solve for this one, but over there, the output depends on the input and previous outputs, which is called? Recursive. Okay, this one is non-recursive, and this one on the right is recursive. And that has a tremendous impact on the effect of these systems. Now, one thing you probably recall about the recursive, the non-recursive ones are very simple, right? Okay, they're very simple to program, they're very simple to deal with, and one other thing you remember is that in terms of stability of a system, what? A non-recursive system is always stable. Okay? Meaning, so here, if you wanted your impulse response for a non-recursive system, you just plug in h of n, the impulse response, plug in place of y, is delta of n minus delta n minus 1. Right? That's it. Done. Step response. The step response, by definition, is just the result of the output when you put in a step. I'm going to call it S of n, is u of n, then minus u of n minus 1. Done. Right there it is. Now, that is not nearly as simple for a recursive system. In fact, you really can't do it. I can plug it in here for my impulse response. I would have h of n, but on the right-hand side, I would have delta of n plus 1.7 h of n minus 1 minus 0.72 h of n minus 2, and that's a very nice equation. It's true, it's mathematically correct, but it doesn't do anything for you. Over there, you've got h of n's delta n minus 1. You've got it right there. That's your impulse response. This gives you a recursion to find the impulse response, but that really doesn't help you find it. And for a second order one, it's not obvious. It would take some work. How are we going to do it, though? We're going to find the impulse response and the step response by doing what? Taking Z transforms. That's where I'm going next. And then we'll talk about transfer functions. Okay? So, let's find the transfer functions. Transfer functions for this system. Transfer function for the recursive system. Not transfer functions, just one over here. Transfer function, we would write y of z is x of z minus z to the minus 1 x of z. You all remember that, don't you? Z to the minus 1 is the unit delay operator. Yeah?
I got a question. Why did you put the signs on this?
Oh, I moved them to the other side. These here,
Oh, okay.
moved them from left to right, so the signs flip on those. Okay? That's all right, just make sure you ask if you have a question. Okay, transfer function over here, and then the transfer function, h of z, by definition, is the transform of the output over transform of the input. Y'all remember how to do that? Don't get the reciprocal. Okay, y of z divided by x of z, divide the x of z terms, move them down here, and you get 1 minus z to the minus 1. So there's your transfer function. Transfer function over here, same thing. We're going to write y of z, and on the left-hand side we'll get 1 minus 1.7 z to the minus 1 plus 0.72 z to the minus 2. And on the right-hand side is x of z, and we're going to do the same thing here. H of z, y of z divided by x of z. And you get what? Tell me what the numerator is. Felt kind of quiet today. What's the numerator? 1?
1.
1. Remember, it's the coefficients of the input. 1. Denominator, 1 minus 1.7 z to the minus 1 plus 0.72 z to the minus 2. And, all right, there's your transfer function here. What do you notice about these two transfer functions? And it is not a coincidence that that one is non-recursive and this one is recursive. When it is non-recursive, what does the transfer function look like? What does that look like as opposed to this? You do not have a denominator over there, right? Turns out it's just a power series in z, or actually it's a power series in z to the minus 1. This one will have a denominator. What does that mean? If that one doesn't have a denominator, it has no... What does the denominator give you? The poles of the system, right? This one has no poles. Non-recursive systems have no poles except possibly at 0 and or infinity. Does that have a pole at 0 or infinity? It actually does, doesn't it? Plug in 0, you get a pole? Yeah, everybody agree? Okay, now, for recursive systems, the transfer function has a denominator. When it has a denominator, that means wherever the denominator goes to 0, you have poles. And in this case, let's write this as z squared over z squared minus 1.7z plus 0.72. And that will give us a rational expression in positive powers of z. I know you all are more comfortable with that, right? Meaning, can you factor that denominator? I think you can. Z squared over z minus z minus. You all do that. Got a calculator? Don't need a calculator, actually. I set it up so it's easy to factor. What is it? Need two numbers that add up to 1.7 and their product is 0.72. 0.9.8, yeah. 0.8 and 0.9. Does that work? 0.8, 0.9 gives, added together, gives you 1.7, and 0.9 times 0.8 gives you 0.72. Okay, so I was hoping, that's what I was had in mind from the beginning, given those coefficients in that difference equation. Okay, so now we've got a transfer function. It has poles. This system has poles at 0.8 and 0.9. Now, remembering back to last week when we were talking about just z-transforms in general, and when a z-transform corresponded to a well-behaved sequence, and when it corresponded to a causal sequence. Does that sound familiar? You remember that? What did that have to do with what being in the region of convergence? Two places. Where? Unit circle and way out there. Infinity. Unit circle and infinity. Okay, so now we're going to find the impulse response and step response for this system. Okay, this is the way we're going to do it. As I said, and by the way, I can do the same thing for the step response here. This is a recursion that the impulse response has to satisfy, and I can do the same thing for the step response, right? S of n, U of n, S of n minus 1, S of n minus 2. Yeah, that's a recursion that it would have to satisfy, but that doesn't give us an expression for it. We're going to find it. And incidentally, are you all recognizing, does this look familiar to you? May have been a semester or two or three. But now, I've already found the impulse and step responses for the non-recursive system. And by the way, for the non-recursive system, you can always do that. It's easy. Will always be trivial. You don't need the Z transforms for that. However, for the impulse response, the input would be x of n would be delta of n, and that means that x of c is what? Z transform of the impulse? One? I remember that, don't you? The impulse function is 1 right there. 0 everywhere else, just 1. And so it's 1. What about the ROC then? I answered that one for you. What about the region of convergence? All Z? Okay, this puts no restriction on the region of convergence. So, now we know if transfer function is y of z divided by x of z, then that means that y of z is h of z times x of z, because that's just an algebraic manipulation. Right? All right, and if x of z is 1, that turns out to just be h of z. So y of z is z squared over z minus 0.8 and z minus 0.9. And I've already multiplied it by 1, by the way, because that was the input was an impulse. All up with me? I'm going too fast? No? Good. All right. So, I want y of n. I want the impulse response. How do I get it? Just because you don't want to do it doesn't mean you can't say it. What is it? Partial fraction expansion? Okay, a question. You remember that the rules for a partial fraction expansion require that the numerator order be less than the denominator order. Except we're not going to expand that. We're going to take out one of the z terms out here and expand that. We can expand that now, right? So, and we need that z so that we can write az over z minus 0.8 and bz over z minus 0.9. And can we use cover-up method for this? Yeah. Right? Only reason we couldn't use cover-up method is if, what? We had repeated poles. Okay? We don't, so we're good. Now, I want you to notice, and remember this, that z that I factored out gets pulled back into the numerators. That z has no impact on the finding the coefficients. So A, we got that z. We still have a z in the numerator, and it's z minus 0.9, and evaluated at 0.8. That's 0.8 over negative 0.1. Negative 8? Is that right? 0.8 over 0.1, 8, negative 8?
Yeah.
Negative 8. Okay? B would be z over z minus 0.8 evaluated at z as 0.9, which is 0.9 over 0.1, and that's 9. Okay, so our answer is this. Y of n is A. A is negative 8, so it's negative 8 times 0.8 to the n u of n, plus 9 times 0.9 to the n u of n. There's our answer. See, 0.9, yeah, 0.9 decays slower than 0.8. Yeah, that's right. Now, if I were to ask y'all to plot that, could you? Plug in a few values. Yeah, you could do that. Is it well behaved? That's what's more important. What do these terms do? 0.8 to the n, what does it do? Decays? 0.9 to the n? Decays? Well behaved, right? They decay exponentially. And it turns out, what do you all remember about stability here? Oh, I left something out about stability. This is interesting. None of y'all complained. You remember a couple of Z-transform pairs. A to n u of n is z over z minus a. Magnitude of z greater than magnitude of a. Do y'all remember that one? That's in the list that we derived last week at some point. But the other one, you should remember this one from 431. Negative a to the n u of negative n minus 1 also has z transform z over z minus a, except that it converges inside the pole. Magnitude of z less than magnitude of a. What did I assume here? I assumed, now at this point finding a and b, it doesn't matter, but in going from this step to that step, I assumed an ROC that was magnitude of z greater than 0.9. In other words, outside both poles. You see that? Now, could I have assumed this region of convergence? I could have assumed either one. Would it have made any sense, though? What if I'd done this one? No, it wouldn't have. Why? Because the term would have been going to the left. And what happens if you have something like 0.9 to the n, u of negative n minus 1? That term, you said 0.9 to the n, u of n, decays nicely. And it's causal, by the way. But what about this one? This one is going to the left. What does it do? If it decays going to the right, it's going to blow up going to the left. And that's not going to be good. So, without saying it, I actually assumed that the region of convergence was greater than 0.9, but that's what we should assume anyway. Okay, we wind up with a well-behaved and causal signal. Otherwise, we would have had a non-causal and exploding signal. There, that wouldn't be good. Okay, step response. Can we do it the same way? And can we do it the same way? Yes? Going to be a little more complicated though. So for this system to find its step response, we would do something like this. X of z would be z over z minus 1, and that one has a ROC outside the pole at 1. True? Is that one familiar to you? Yes. Don't yawn. Don't yawn. It's too late in the day. I don't want to get that started.
Not because we wake up so early in the morning.
Well, I know you all been working today, right?
Yeah.
Okay. So, but the technique is going to be the same. It's going to be more complicated, though, because the Z-transform of the input, if it's a step, it's more complicated than an impulse, right? So now we're going to have y of z is z cubed over z minus 1, z minus 0.8, and z minus 0.9. Is that right? We picked up another z in the numerator, we picked up a pole at 1 in the denominator. And can we still partial fraction expand it? Yes, we can. So we'll write it as a z over z minus 1, b z over z minus 0.8, and cz over z minus 0.9. Can we find A, B, and C by the cover-up method? We can. Yeah, no repeated poles. Excuse me. Is the order all right? Let me just make sure we understand how we're doing this. The A, we would find, and I am going to find A, because A is more important to me than B and C, and you all should know why. A is going to be C squared over C minus 0.8 and C minus 0.9, and I'm going to evaluate it at the poles, Z equals 1. Okay? Why do I have a Z squared in the numerator? Why don't I have a Z cubed? Why don't I have just a 1?
You already have
What? Because I pulled one of the Z's out to keep in there, and that left Z squared. So what I'm really partial fraction expanding is that. I took the Z out and then I put it back in. Okay, and I am going to evaluate this. What is that? 1 over 0.2 times 0.1. That's a big number. 50? Is it? Is that right? Okay, thank you. 50. Okay, so y of n is, what's the first term? Z over Z minus 1, step function. 50 u of n plus b times 0.8 to the n u of n, and c times 0.9 to the n u of n. Okay, there's my answer. Why did I find A? I wanted to do one of them just to make sure we understand how to do it. Why did I find A? A is very important. What does it represent? Let's go back to controls.
First order.
What?
First.
If it is decaying, won't, because it's the largest term, won't they all be?
Which one?
If A.
Is A
largest
decaying?
impact,
Is A decaying?
no.
No, it's not.
Stable.
No, it's not right now, but I'm
Stable.
saying it has the largest impact. If A is, like if the later ones are exploding and A is
Now, if anything's exploding, it's just exploding. That doesn't, yeah.
Okay.
But you're on the right track. What are these two doing?
Decaying.
The
0.8 to the n, 0.9 to the n, what do they do?
Decaying.
They're decaying. These are what we call transients, right?
Gensens and the first order.
So what's the first one?
Stable.
steady state.
Steady state,
Steady
transients.
state. Yeah.
Here's your steady state term, and A is actually the final value.
Okay.
Yeah.
I didn't want to do all of them because I'm lazy, but I did want to do one of them so you could see it done. And so of the three, B and C represent transient terms, so I did A to show you that's what you're going to wind up with in steady state, because the other two terms will decay. Right? And you all remember what I was getting at with the controls was we learned to identify steady state and transient terms. Okay, so, I did it again. I went from this expression down to here, and I assumed that the ROC was magnitude of Z greater than 1. Without even saying it, I assumed that. Did I assume that? Could I have chosen anything else? Could I have chosen anything over here? I could have. Let's go back real quick. This expression right here is poles at 0.8 and 0.9. What ROCs could I have chosen? Outside both, greater than 0.9. 0.8, less than magnitude of Z, less than 0.9, that's a toroid or a donut-shaped region. Or magnitude of Z less than 0.8. I could have chosen any of those, couldn't I? Which one did I choose? And I'm emphasizing choose. I chose this one because it contained, what'd you say, Hudson? Unit circle and infinity. Okay? Unit circle made it well-behaved. Infinity made it causal. That was good. So I actually chose this one here.
The circle.
But over here, where do we have poles? We have poles at 0.8, 0.9, and 1. So it appears that we could have this, magnitude of z greater than 1, 0.9 less than magnitude of z less than 1, 0.8 less than magnitude of z less than 0.9, or magnitude of z less than 0.8. It appears that I could choose either one of them, but I actually didn't get to choose it. Why not? When I took this, said we're going to do step response, first thing I had to do was find x of z. What's x of z?
It's bigger
Right
than
there? And what's the ROC of x of z?
C bigger than 1.
That. I didn't get to choose it. I cannot use any of these others. That was already chosen for me. Why did that not, was that not an issue over here? Because the impulse didn't put any restriction on z. So over here it truly was a choice. Now, it wasn't a very hard choice because to make it well-behaved and causal, it needs to be outside the biggest pole there. But over there, it was not a choice. As soon as I took the z-transform of the step input, magnitude of z greater than 1, that's the only choice I have. I can't change it. Okay, so, good so far? All right, I'm going to do another example. And this one, for this one, I want to have a difference equation. I want to do a couple of calculations over here. Well, I have to walk over to the side and use MATLAB just for a second. And I'm not going to turn over the. I'm not going to turn on the projector because I don't want you to see what I'm doing. Cheating is what it's called. I'll tell you in just a second. Come on. All right, 1 minus 1 point, you all remember these numbers. 1, negative 1.663, and 0.81. All right, so my next difference equation is going to be this. Y of n minus, what was the second number?
1.663.
1.663, y of n minus 1. Third number,
0.881.
0.81.
0.881, I think.
For
Above
A1.
0.1.
I thought for
I think-
A1.
I think I meant 0.81.
Yeah.
Okay, y of n minus 2 equals x of n. Okay, and I'll tell you why. The poles of the system are going to be at 0.9 e to the plus or minus j pi over 8. Okay, don't worry. In just a few minutes, I'm going to show you how to do this. We're going to need some results from MATLAB. So, can we find the transfer function? And the answer is, of course, we can. Oh, one other thing. Let's make this x of n minus, or plus x of n minus 1. Okay, that'll make it work out better. So, transfer function, h of z, numerator, input terms, what are they? 1 plus z minus 1. Denominator, 1 minus what? 1.663 z to the minus 1 plus 0.81 z to the minus 2. Okay, and by the way, we got this from a difference equation. There is no region of convergence on that. We can choose a region of convergence. We'll get to it. But I want the impulse response of the system. And the impulse response is found by setting x of z is 1, because x of n is a delta function. And so y of z equals 1 plus z to the minus 1, 1 minus 1.663 z to the minus 1 plus 0.81 z to the minus 2. Don't ask me why I'm repeating that. Same thing as above. And we've got a bit of a problem. But this is not it. Z times z plus 1. The denominator could be written this way. I know where the poles are. How do I know the poles? Because I made up the problem. What if I didn't already know that? I could use MATLAB to find it, couldn't I? We're going to do that in just a minute. Okay, denominator z minus 0.9 e to the j pi over 8 and c minus 0.9 e to the negative j pi over 8. Is that what poles mean? Can I factor it like that? Remember, those exponentials are 0.9 magnitude e to the j pi over 8 face. Pi over 8 is the face of the poles. So, excuse me. Well, that looks kind of intimidating. But here's what we're going to do. I'm going to solve this one symbolically, and then we're going to go back and plug in the numbers. What do you remember? What does that look like? That's going to be of the form 0.9 to the n cosine pi over 8n. Remember that one? I'll write it on the side over here, because this was a part of our table that you all were supposed to memorize last week. If we had a to the n cosine omega 0 n u of n, the z transform was z times z minus a cosine omega 0 over z squared minus 2a cosine omega 0 z plus a squared. Do you remember that one? Now, its cousin that we didn't do was a to the n times sine omega 0 n u of n. And this one turned out to be az sine omega 0, if I remember correctly, over z squared minus 2a cosine of omega 0 z plus a squared. All right, what do you notice? The difference between those two is where? Difference between those z transforms? In numerator? The denominators are the same, which means if the denominators are the same, they have the same poles, right? Okay, now I know where the poles are, and I just made up that numerator. Okay, I made up the right-hand side, x of n plus x of n minus 1. And I'm betting, I know for absolute certain it doesn't fit that form, and I'm pretty much assured it won't fit that form. No, there's no way on earth that it would fit that form. So what do I have? I have some combination of the two, right? Have some combination of the two. And I tell you what I do not want to do. I do not want to try to split that numerator up and do some massaging on it and try to get it in that form plus that form. That is going to be a mess. But I'm going to show you a little trick here to invert the z transform on an expression like that. So let's say that we have the following. And as I said, I'm going to write this one out symbolically, so that when we're done, not only will we have the answer to this problem, but I'm going to give you a formula that you can use in general when you have complex poles. So let's say that we have a y of z is, let's say it's z times z plus 1. I'll keep the same numerator. And in the denominator, okay, in the denominator, I'm going to say it's z minus r e to the j omega. and z minus r e to the negative j omega. What do you notice about those poles? They are, the poles are at r e to the what?
Plus or minus.
Yeah, plus or minus j omega. They're complex conjugates. Will they always be complex conjugates? Yes, they will. If the coefficients are real and we don't deal with complex valued coefficients. Coefficients will be real, therefore the poles will be in complex conjugate pairs. Can we do a partial fraction expansion like this? A z over z minus r e to the j omega plus b. If you're taking notes in ink, don't write the second numerator, okay, because I'm going to change it. Over z minus r e to the negative j omega. Could I do a partial fraction expansion like that? Actually, I can. There's nothing says that those poles have to be real. Okay? They can be complex, and they are. How are the poles related? They are complex conjugates, right? This is why I said that about taking notes in ink. If the poles are complex conjugates, I'm not going to prove this, but it turns out that those coefficients will actually be complex conjugates. Okay. They're not necessarily easy to find. Can you still use the cover-up method? Yes, you can. But you're dealing with complex numbers here, and it makes it a nuisance. On the other hand, how many coefficients do you have to find? Just one. You find A and its conjugate, you know how to get its conjugate then. So you only have to find, it is a complex valued coefficient. It's a nuisance to calculate even with a calculator, but you only have to find one because the other one is just its complex conjugate. Okay? So, what do we have when we're done? Let's assume that the ROC is magnitude of z greater than r. In other words, outside the poles, which guarantees it'll be causal, and if r is less than 1, it'll also be stable, won't it? Because that would include the unit circle. Okay, so, bear with me. This is 3 or 4 steps of algebra, but it's just algebra. So y of n, I'm going to write A as magnitude of A e to the j theta. Can I do that? What have I done? All I've done is write it in polar form with a magnitude and a phase. Magnitude e to the j phase. So, now, what I have is then magnitude of A e to the j theta z over z minus r e to the j omega plus magnitude of A e to the negative j theta z over z minus r e to the negative j omega. Are we all on the same page here? See where I'm getting this? Now, each step I do, I'm doing very little work, but I'm not leaving out any steps here. So, what have we got? Don't need that anymore. Y of n is, I've got a constant up there, magnitude of A e to the j theta. What is z over z minus something? A to the n, right? This is what we've been calling little a. So that'll be times r e to the j omega to the n u of n. That z over z minus a, we've been treating it most of the time as if a is real, and it works, but a doesn't have to be real. And here, a is r e to the j omega. What am I going to get for the second term? Y'all tell me. We're over there. Magnitude of a, what?
E to the negative j theta.
E to the negative j theta, and then r e to the negative j omega to the nth u of n. Now, you notice that there's some terms here that are going to be common. And we're going to factor them out. And then we're going to massage what's left. So one common term is magnitude of A. E to the j theta is not common.
U of n.
These terms, this is going to be r to the n e to the j omega n, and this one is going to be r to the n e to the negative j omega n. What do you get? Another common term? R to the n, okay, times r to the n. And then it will give us this term e to the j omega n, and I'm going to factor the u of n out on the right-hand side. Oh, no, I left something out, didn't I? I left out e to the j theta. E to the j theta times e to the j omega n. Tell me if you agree with that first term. Multiply them back out. Is it the same? All right? Second term, what do we get? You all tell me. I factored that out. I factored the r out.
U to the negative
E to
j
the negative
omega
j theta
theta
times e to the
negative j omega.
negative j omega n u of n. Do you see how this is all about to fall out?
Kind
Yeah. What? Okay. So what we've got left-hand side, magnitude of A, r to the n. This becomes e to the j omega n plus theta. And what's the next one? E to the negative j omega n plus theta. How about that now, Connor? U of n. What's in square brackets there? Euler's formula? Yeah, what is it? E to the j plus e to the minus j, 2 cosine, right? So here is the final, yeah, this is going to be the final answer. So it is magnitude of A, r to the n, times 2, I'll put it up front, cosine of omega n plus theta times u of n. And there's the final answer. What happened to the numerator? Where'd the numerator go? That z times z plus 1? Well, first thing, the z stays in here, but what about the z plus 1? It becomes a part of the coefficients when you do cover-up method. And you may be saying, I really don't want to find these coefficients. Okay, you took the right class, because I'm not going to make you find it. I'm going to show you how to do it in MATLAB. All right? Now, the final result. Tell me, thankfully I have some colored markers here. The poles are at r e to the plus or minus j omega. Okay, that's in red. The coefficients are magnitude of A, e to the plus or minus j theta, right? By coefficients, I mean partial fraction expansion coefficients. Okay, what happens here? Tell me as I go through every one of these terms where it comes from. Red is where the poles are. Green is for the coefficients that I find. You've got a constant out front, just a constant. Where does it come from? That's the coefficient, magnitude of A. This coefficient up here. All right, you've got an r to the n. What's that going to tell you? How fast it decays. Where does that come from?
Poles.
Pole? Yeah, pole. Okay, that's from a pole. Cosine. You've got a frequency. How fast it oscillates. Where does it come from?
Poles.
Pole. And there is an initial phase shift there in that sinusoid. Where does that come from?
Coefficient.
That comes from a coefficient. That comes from right there. And now you say, does that really help me? The answer is yes, it does. I am going to write that example that we've been working on. I'm going to write it over here now. And the reason I'm going to write it over here is I'm going to lower the screen and show you how to do this with MATLAB. So I have z times z plus 1 over z minus 0.9 e to the j pi over 8 and z minus 0.9 e to the negative j pi over 8. But I'm going to go backwards here. What I've got is 1 plus z to the minus 1 over 1 minus 1.663 z to the minus 1 plus 0.81 z to the minus 2. And so I will let you write down what I'm typing, because now I'm going to show you what I was typing over there. Or now I'm going to show you what I am typing. So I want to go over the screen and see if I can get this projector to come on. Good. It's on. I hate lecturing from the side over here, but you all watch over there, and I'm going to type over here. And so, notice this. That second form down there is in terms of negative powers of z, right? That's the one I'm going to use. And is it coming on? Yes, it is. Okay, so my numerator is, I'm going to start from the constant and then drop down in powers of z. 1 and 1, is that it? Is that it? Okay. And, all right, denominator. I've already got that denominator in there, don't I? 1, negative 1.663, and 0.81. All right, so now, left-hand side, square bracket,
In the
r
bracket.
comma p comma k equals, it's going to, this routine is going to return 3 variables. On the right-hand side, residue. Y'all remember the term residue when you're working with Laplace transforms? We're not doing it the same way here. This is residue z. And incidentally, if you are y'all familiar with the term residue? In this context, I mean. Residue is the mathematician's term for partial fraction expansion. We call it partial fraction expansion, and then in like Calc 2, where we study this, the mathematicians just humor us engineers and call it partial fractions. But mathematically, the correct term is residue. And because I'm doing residues for Z transforms, that's a different partial fraction expansion than for Laplace transforms. Okay, it's called residue Z. And in parentheses, numerator, comma, denominator. And we're going to get a whole bunch of answers here. Okay? Do you see those answers? I'll write them down on the board for you. Notice something. At the bottom, you get K is empty. Square bracket, square bracket. There's nothing in it. That should always be the case for all the examples we're going to do. If we ever need to know what that means, I'll tell you later, but we shouldn't need to know that. But we've got this, R. R is 0.5 minus J, 0.5 plus or minus, oh no, it's not. It's minus or plus. It matters, believe it or not. Minus or plus J 2.66 apparently. 2.66. What it means, I'll show you in a minute. P is 0.83158315. this one's plus or minus. J 0.3441, is that correct? No, 3.444. 0.8315 plus or minus. Don't overlook that plus or minus versus minus plus because it matters. Okay, what does this mean? R stands for the residues, which we call partial fraction coefficients. P stands for the poles. Okay? Now, I'm going to go back over and type some more. Why? Because those residues and poles are in rectangular form. I want them in polar form. So, ABS of the poles, absolute value of the poles. Whoop, wait a minute, what did I do? Turned the bracket wrong. Okay, are you surprised by that? 0.9? That's what I told you I was starting with. Radius 0.9 for the poles. Angle of the poles, and I'm going to do the angle divided by pi. 0.125. Do y'all recognize the number 0.125? It's 1/8. Right? It's 1/8. And so what I just calculated there says that my poles are at 0.9, 0.9 e to the plus or minus j pi over 8. Is that what I said I started with? And you got to be careful. I knew it was pi over 8 because I set the problem up. You wouldn't know it's pi over 8. You need to calculate it. Turns out it's whatever that is, 0.125 pi. Is it positive first in MATLAB? Yes? Okay, so I'm going to do the same thing. I've got my poles, and I verified where the poles are. I already told you that's where they were. I knew that from the beginning. Okay, but my residues, I want them in polar form. Absolute value of R, ABS of R, and angle of R. And I'm just going to leave it as in radian form. All right. Magnitude of those coefficients, 2.705, 2.7054, and angle. E, tell me what to write now. E to the what? Where's the angle up there? You got it? You see it?
Minus plus.
Yeah. What'd you say?
Minus plus.
Yeah. Can I say plus or minus? No, I cannot. It's negative or positive 1.3849. Negative, positive, J 1.3849. And here's why I cannot. I wrote the first pole Z over Z minus R e to the J omega. Y'all are going to tell me what R, omega, J, not J, I know what J is, A and theta are. I wrote that as magnitude of A e to the J theta with this one. So look at those. The first pole is R e to the J positive omega. Positive omega is positive pi over 8. That's the first one. Right? And by the way, R is 0.9. Okay, now, to go with that, can you tell me what magnitude of A is?
2.7054.
2.7054. Can you tell me what theta is, and be very careful? What?
1.3849.
Positive or negative?
Negative.
Negative. Negative 1.3849. Why does it matter? the order that MATLAB does those, the order that it finds the poles is the same order that it gives you the coefficients. So this one is plus or minus, so the positive pi over 8 goes with the first one there, the negative angle. And so after all these calculations, after all this explanation, here's the final answer. Y of n is 2, magnitude of A, 2.7054. R to the n is 0.9 to the n. Cosine omega is pi over 8. N and theta is minus 1.3849. And I don't want to forget the u of n at the end. And I am done. And if you think that's painful, try doing it by hand. It's much worse. That'll get you through a lot of those problems. Okay? We good?
That's the impulse response.
That is, yes, that is the impulse response.
Right.
Okay, now I'm going to show you real quickly, in the next 10 minutes, I want to show you how to do step response for this system. Okay? Step response, interesting, useful. All right, all that's done. For the step response, and I'm not going to fill in all the details, but I just erased the answer there. Hope you got it. Y of z is 1 plus z to the minus 1, denominator 1 minus z to the minus 1, 1 minus 1.663 z to the minus 1, plus 0.81 z to the minus 2. And here's what I just did. I took h of z and multiplied it by 1 over 1 minus z to the minus 1. Is that what I did? H of z times that. And there is x of z. Because x of z, because the input was a step. Yeah, I'm finding a step response. The input was a step. Now I want to show you real quickly how to do the same thing here. And we're going to come up with an answer with a time domain function. And we're going to do it without any pencil and paper work, and that's a good thing. All right, my numerator, in this case, my numerator is 1 and 1, is that correct? Yeah. My denominator, look at this, DEN, what was it? 1.663.81. That's a part of what I want for the denominator, isn't it? Do you agree? Yeah, but what do I need to do? I need to multiply it by 1 minus z to the minus 1. So, I'm going to say my new denominator is CONV, the old denominator with 1 and minus 1. Do y'all remember the CONV command for multiplying polynomials? By the way, did I show you all that trick in 431? Do you remember? I'll show you in a minute. Here's how you multiply polynomials. Let's just say that for right now. And so if I multiplied it out, there's my new denominator. It would be 1 minus 2.663 z to the minus 1 plus 2.473 z to the minus 2 minus 0.81 z to the minus 3. And by the way, check like the first to the last numbers. That's easy to do. And you'll see that that's the right answer. Okay. Here we go. RPK. Square bracket R comma P comma K equals residue Z, numerator denominator. K is still empty. Good. Because we don't know what to do with it if it wasn't. All right. Here's what it says. The first term is z minus 1, isn't it? Because the pole is at 1. I'm doing them in order. P stands for pole. Pole at 1. The second one, that's going to be z minus, we already did that conversion, didn't we? The poles are the same as they were before. This is 0.9 e to the j pi over 8. And the next one is something over z minus 0.9 e minus 0.9 e to the negative j pi over 8. And I've got z's in the numerator of all these. Can you tell me the coefficients for the numerator? Yes, you can. One of them, what? Read down the list of residues, the R's.
13.
13.6 right here. 13.6. Okay? And now, I want the other coefficients in polar form, right? So, here we go. The R's. One thing right now, I don't have to do the poles in polar form. I already know the one with the positive phase angle is first. So it's R e to the, it's 0.9 e to the j pi over 8. 0.9 e to the minus j pi over 8 is the second one. So I'm just going to work with the residues. Magnitudes of them. And I've already got the first one, it's 13.6. Done with that. ABS of R and angle of R. Now, what we got? ABS, 6.35. So this one is plus 6.35. E, what's the angle? Negative 3.018. Negative 3.018. And the other one is what? 6.35, e to the negative j. 6.35 e to the positive j, 3.018. Notice we haven't had to do any real pencil and paper work. All we're doing is writing down the results from MATLAB. So, why then? You all tell me what this answer is, and we'll go home. What's the very first one? C over C minus 1. What is it? 13.6. U of n? That's your step, right? Okay, the rest of it. 2, 6.35, right? 0.9 to the n, cosine, who? Pi over 8 n, and what's the angle? Minus 3.018, and U of n, and there's the final answer. Okay. Don't bother memorizing that formula. You're not going to have any closed book exams. You don't have to memorize it. Just know how to use it. And know how to get what you need from MATLAB. Just be very careful. As I said, you got to notice the positive phase angle on that pole went with the negative phase angle on that coefficient. And that was this one. Oh, what does the 0 on there mean? That was the first coefficient, 13.609.
No phase, or no angle.
Phase angle, right. That phase angle will either be 0 or pi. In other words, that coefficient will either be positive or negative. A phase angle of 0 is out the real axis. A phase angle of pi is the negative real axis, which means it's negative. So we don't need to talk about that. What about these two terms? Steady state, transient, both, neither?
Steady state.
There you go. Steady state. And this term is transient. Is it really transient? Why is it really transient? because of what term? I'm gonna point to them, you tell me why it's transient. Nope. Nope. That one. Y'all say that one. Yeah, and that's it. 0.9 to the end is gonna cause it to damp out and go away. And when all is said and done, the step response will wind up at 13.6. That's where it's gonna stay. Okay? All right, we're done. Y'all can
Did you write about the MATLAB?
go